Okay, good morning, class. Hey, sorry that I'm missing class today, but I want to get through at least most of the rest of section 19.2. And in this section, we're going to be covering other kinds of surfaces that are not in the form of z as a function of x and y. So for example, suppose we have a surface that's defined as y is equal to 1 minus x squared. All right, so this is going to be a surface, but this surface is going to be, the graph of it is going to look something like this. This is the x and the y plane. This parabola is going to be a parabola that opens downward, and it's going to look something like this in the xy plane. And then let's say that z, let's say, goes up here to 3, and our surface is going to look something like this. All right, so here's the top edge of it, and it has this kind of a form. All right, so what I'd like to be able to do then is find the flux over a surface that looks something like this, and let's say that the orientation is in the positive y direction. All right, so orientation is out this way. All right, and let's say that our vector field F is defined as y times z times I plus y times j plus x times k. All right, so the question then is to find the flux outward or in the positive y direction by this vector field over this surface. All right, so we're not going to do anything that's that much different here. We're going to parameterize the surface, and the parameterization is what's going to be a little bit different in this case. All right, so we've got y defined in terms of x, so maybe we want to start with that and say let y be equal to 1 minus x squared. And then we can say x is x, and we can say that z is equal to z. So we're going to parameterize the surface in terms of x and z. And then the other thing I want to look at is what does this look like then in the xz plane. All right, so if x is here and z is here, and we imagine what our footprint or our shadow looks like, the shadow is going to be not this parabolic shape down here. It's going to end up being this rectangle that we see in the xz plane. All right, so that rectangle is going to have bounds on x that are going to go from -1 to +1. Okay, that's these bounds. And then on z, it's going to come up to 3. All right, so our boundary is going to look something like this. All right, and then like we did before, let's think about, we're going to pick a point that's on this plane. That's going to correspond to a point in the xy plane, which corresponds to a point that's on the surface. And then like we did in the early part of section 19.2, we said what happens if we move in the x direction here? Well, as we move in the x direction on this surface, we're going to be kind of wrapping around this parabolic shape. And then if we move in the z direction, okay, move upward here, we're going to end up just moving upward along this surface. All right, so to find the dA, all right, we're going to have to take the cross product of Rx and Rz, and again we have to think about what order we're going to do those in. We want the orientation to be outward, so if we take the cross product of these using the right hand rule, I think we want to take the green vector and then cross it with the red vector. So that green vector is Rz and the red vector is Rx. All right, so Rz is going to be the derivative of these with respect to z, which will just be 0 and 0 and 1. And with respect to x, we're going to get 1 and minus 2x and 0. All right, then take the cross product of those two, and we're going to get the I component will be 0 minus negative 2x. All right, so it's going to be 0 and then plus 2x is going to give me 2x. The I component is going to be 0 and then minus 1, and then I have to change the sign on that. And then the k component is going to be 0 minus 0 is 0. Alright, so the dA on this one is 2x, 1, 0, and then the differential is just dx and dz. Alright, then also we want to find this vector field in terms of just x and z. So y is going to get replaced with 1 minus x squared. So this would be 1 minus x squared times z. Y is again going to be 1 minus x squared, and x is just x. Alright, so then to find the flux over this surface, we're going to set up a double integral of the dot product of f and dA. So we're going to take the dot product of these two, and we're going to get, guys, this is going to be z times 2x, so 2xz. 2x times z times negative x squared is going to give me negative 2x to the third times z, and then 1's going to get multiplied by 1 minus x squared, and then dx and dz. Alright, my limits on x are going to be from negative 1 up here to positive 1, and my limits on z are going to be from 0 to 3. Alright, and I'm going to leave this for you to evaluate. Okay, once we get to this point, that should be fairly easy to evaluate for most people. Alright, so we're not going to do anything that's much different here, except that our parameterization is going to take care of what happens if the surface is defined a little bit different way. Otherwise, we're doing exactly the same kind of a process. Okay, now the other thing that's in this section is what if your surfaces are not in the form of one variable is equal to a function of the other two? And let's look at what happens if we have a surface that is defined as, let's say, x squared plus y squared is equal to 4, and let's say that we have z is bounded by 0 and let's say 3. Alright, so this is going to end up just being a cylinder. Alright, so this cylinder is going to look something like this. Alright, it's going to have a circular region in the xy plane. That circle is going to have a radius of 2. And the cylinder is going to go up the z-axis, and it's 3 units tall. Okay, so this comes up here to 3. This has got a radius of 2. Alright, and let's say the orientation is outward, okay, away from the z-axis. Alright, now the cylinder doesn't have a top or a bottom. This is just going to be the round part of the cylinder, and we want to calculate the flux over this surface. Alright, I'm going to show you two ways to do this. One way, the first way is the way that I would approach this, and then the second way is the way the book approaches it. And I think that there's going to be some very similar parts to these, but I think the way that I do it is going to connect with what we did earlier in section 19.2. Alright, so the idea then is to parameterize the surface. Alright, and the problem is that this is not just a function of x and not just a function of y. This is a surface that's defined as a function of 2 or 3 variables is equal to a constant. And I think at this point we should be thinking about parameterizing this a little bit different way. Alright, and the way that I want to do this is to go back to the stuff that we did with cylindrical coordinates and think about how we parameterize a cylinder. Alright, so if you remember from cylindrical coordinates, x was equal to r cosine theta. Alright, the radius on this is always going to be equal to the same number, 2. So 2 cosine of theta, and y is equal to 2 sine of theta, and then z is just going to be equal to z. Alright, so there's the parameterization of this surface in terms of just theta and z. Alright, so then the next thing that we looked at was, well, what does this look like in the plane whose axes are the parameters? Alright, and the parameters are theta and z. Alright, and what we see here does not really show up much over here. We just have to think about what the limits are on these parameters. Theta is going to be measured in a counterclockwise direction going around this circle, and so theta is going to go from 0 to 2 pi, and then z is going to go from just 0 to 3. Alright, so this is the plane that contains our parameters. Alright, now from here I want to be able to come up with the area vector. Oh, and I forgot to tell you that the vector field F, let's say the vector field F is defined as x, I, plus y, j, plus x plus z times k. Okay, so like we did before, let's think about, here's a point that's on the surface. That's going to correspond to some point that is on this surface. And again, we want to think about what happens if we move in the, this would be in the theta direction. So theta is going to go around this thing in a counterclockwise direction. So as theta increases, this point would move kind of in that direction. All right, and then as z increases, as we move up in this plane, we're going to be moving up in this plane. Okay, so I think what I want to do here is take the cross product of these so that I get a vector that points outward. So I think I want to take the red vector and then cross it with the green vector. All right, and that red vector, I think I would refer to that as r theta, and then the other vector would be rz. All right, so r theta is going to be the derivative of these with respect to theta. So derivative of 2 cosine will be negative 2 sine theta. The derivative of 2 sine is 2 cosine. And the derivative of z is 0. And then with respect to z, the first two are going to be 0. And the last one is going to be 1. All right, so take the cross product of this to get the area vector. So dA is, let's see, the I component is going to be 2 cosine theta. The j component is going to be negative sine minus 0, and then remember to change the sign, so 2 sine theta. And the k component is going to be 0 minus 0 is 0. All right, so the dA is 2 cosine theta, sine theta, and 0. And then the differential in this is going to be d theta and dz. Okay, so then we also need to take this vector field and change these to the parameters. So this vector field is going to be x is 2 cosine theta, y is 2 sine theta, x plus z is 2 cosine theta plus z. All right, and then we're going to set up a double integral of the dot product of these two. So this is going to give me 4 cosine squared theta. I forgot a 2 in here. Yeah, there should be a 2 here. Plus 4 sine squared theta, and then 0 times this is 0, and then we've got d theta and dz. All right, and then to find my limits of integration, I'm going to go back up here to this plane. Theta is going to go from 0 to 2 pi, and z is going to go from 0 to 3. All right, and then I've got a fairly simple integral to evaluate, because this is just going to give me 4 d theta dz, 0 to 2 pi, and from 0 to 3. Okay, and when you evaluate this one, you're going to end up getting, I think, 24 pi. Okay, so this is the way that I would approach this problem, and I like it because you're going to take care of the parameterization up here. Okay, so that's going to be the part that's different. Everything else is going to kind of flow the same. You're going to draw the picture, think about what's happening as you move around in this plane. What does that do on the surface? Find a cross product that's going to produce an outward normal. And then it's just going to be the same. Just take the vector field and dot it with the dA, and then integrate over your limits on the parameters. All right, now I'd like to look at the way the book approaches this. And I like the way that it does it, because when we get to spheres, I think it's going to make a lot more sense. All right, but if we go back and do the same problem and think about it this way. We started out with the surface x squared plus y squared is equal to 4. and z was from 0 to 3, right? And this is going to produce exactly that same cylinder. All right, so we get a circle of radius 2 in the xy plane. This cylinder is 3 units tall. So we get a picture that looks something like this. All right, now the parameterization on this is going to be the same. Okay, x is going to be equal to 2 cosine theta. Y is equal to 2 sine theta. And z is equal to z. All right, we can't get away from that. We're still going to have that same parameterization, which just comes from cylindrical coordinates again. Okay, now the way that the book is going to do this differently is they're going to think about, here is a patch that is on this surface, and we're going to think about how that patch is formed. That patch is going to be formed by something like that coming out of the origin. All right, now one thing that we need to take advantage of is that this expression up here is in the form of g of x, y, and z is equal to a constant. Okay, a vector that is going to be perpendicular to this plane is going to be the gradient of g. All right, and if you take the gradient of this, you're going to get the derivative of x squared is going to be 2x. The derivative of y squared is 2y, and the derivative, there's no z in here, so that's going to be just 0. All right, so this is the gradient. This is a vector that points perpendicular to the surface. So this vector is pointing outward like this, okay, which is the direction we want. All right, now you can also say that a vector that also points in this direction, I'm going to say, how about just x, y, and 0? It's just a scalar multiple of this one. I'm going to use this instead. Okay, so now the other thing that I want to look at is coming up with this delta A. Delta A is going to be a vector that points outward whose magnitude is the same as the size of this patch. Okay, and to find the size of that patch, I want to think about what are the dimensions of this rectangular region. This side, I'm going to say, is a change in z. And then from what we did in polar coordinates, this side is going to be equal to the radius of the cylinder, which was, in this case, 2, and then times delta theta. All right, so the area of this thing is going to be 2 delta theta times delta z. Okay, that's the area of the patch. And it's going to be pointing in this direction. Right, now, if you remember what we did to find a vector that points in this direction that has this magnitude, we said, let's make this a unit vector. All right, so to make this a unit vector, we're going to look at x and y and 0, and we're going to divide that by its magnitude. Well, the magnitude of this vector is going to be the square root of x squared plus y squared. All right, now I'm going to go back up here to the parameterization and write that as 2 cosine theta and 2 sine theta and 0. Okay, and then the denominator is the square root of x squared plus y squared. All right, that's just going to be equal to the radius of the cylinder, which is 2. All right, so we're going to end up with the dA is going to be what happens when I divide all this by 2. So essentially the 2's are all going to cancel out. And we're going to end up with the number that goes in here is going to be just cosine theta, sine theta, and 0. Okay, and then we've got 2 times d theta times dz, and this is my delta A. Okay, so we're also going to look at the vector field F. F is the same vector field that we had before was this one. Okay, so my vector field is going to end up being exactly the same because my parameter is the same here. So we're going to have from before 2 cosine theta, 2 sine theta, and 2 cosine theta plus z. Okay, and then dA is from up here is cosine theta, sine theta, and 0, and then times 2 times d theta times dz. All right, and then if you set up the integral for this one, you're going to have a double integral. This is going to give me 2 cosine squared theta plus 2 sine squared theta. This is going to give me 0, and then we've got all of that times 2 d theta dz. Theta is going to go from 0 to 2 pi, and z is going to go from 0 to 3. All right, and if you compare that to what we had before, this is what we had before, and if you distribute that 2, you're going to get the 4 in there, and you're going to end up getting the exact same answer. All right, but the idea here is to kind of take advantage of this part. All right, we don't have to work quite as hard. Well, I should say it's about the same amount of work for cylinders, but I think it's going to be a lifesaver when we get to doing this for spheres. All right, so in general, when you end up with a cylinder that's oriented this way I mean is running parallel to the z-axis. Okay, your general formula is going to be that you're going to set up a double integral. It's going to be f is going to be in terms of your parameters will be in terms of theta and in terms of z and some kind of a function of theta and z. Okay, all right, which is basically just going to be in terms of the radius of the cylinder, and then we're going to dot that with. All right, well, this thing is going to turn out to be the same thing all the time. It's going to be cosine of theta, sine of theta, and 0, and then times this number r, which is the radius, and then just d theta and dz. All right, so if you are one of those types of students that likes to memorize things, this is a way that you can memorize this. The problem with this memorization is that this works when your cylinder is oriented this way. If your cylinder runs parallel to the x-axis or parallel to the y-axis, you're going to have to make some adjustments in your equations. Okay, so let's take a look at another problem involving cylinders. So let's say that we have a cylinder that runs parallel to the x-axis. All right, so it looks something like this. And let's say that this is a unit circle in the YZ plane, and in the x direction, let's say that this comes out here to 4, and so the cylinder is 4 units tall and it's in the x direction. Okay, if you guys are like the rest of my classes, I think you like the first method better than the second method. All right, so I'm going to proceed with this one with that same method. All right, and think about parameterizing this surface. All right, so now the equation of this sphere is going, or this cylinder is going to be, sorry, not x. This is going to be y squared plus z squared is equal to 1, and x goes from 0 to 4, and let's say that our vector field f is defined as xi plus yj. Sorry, scratch that. Looking at the wrong problem. F is x plus y squared. I plus xj plus let's do yz or yk. Okay, so the parameterization x, y, and z. All right, I think what I want to do is let x be x, okay, because in the yz plane I have the circle. So in the yz plane, let's say that y is equal to the cosine of theta, 1 times the cosine of theta, and 1 times the sine of theta. Right, and then look at what happens in my theta and x plane. Alright, so there's going to be limits on these two. Theta is going to go all the way around the circle, so this will go from 0 to 2 pi, and x is going to go from 0 out here to 4. Alright, like we did before, there's a point that's in this plane is going to correspond to a point that is on the surface. Okay, as theta increases. Alright, now the way that we've got this set up, we're going to be going around a circle in a counterclockwise direction, and that circle is this one. So as we move around this in a counterclockwise direction, this is going to move kind of around the circle that way. And as we move in the x direction, it's going to be moving parallel to the x-axis, comes out this way. All right, and then what I want to do from here is find out which order do I do the cross product in. So if the orientation on the cylinders is typically going to be outward, so I think I want to take the red vector and cross it with the green vector. So the red vector is r theta, and the green vector is r x. Alright, so r theta is going to be the derivative of these with respect to theta will be 0, negative sine theta, and cosine theta. And with respect to x, we're going to get 1, 0, 0. Okay, take the cross product of these, and you're going to get the I component will be 0 minus 0. The j component will be 0 minus cosine, and then change the sign, so positive cosine. And the k component will be 0 minus negative sine, or sine theta. Alright, so the dA is going to be 0 cosine theta sine theta times, and this will be d theta and dx. Okay, the vector field, on the other hand, is going to be x plus y squared will be x plus cosine squared theta. X is x, and y is cosine theta. Alright, then we're going to take the dot product of these two, and you're going to have a double integral. 0 is going to get multiplied by x plus cosine squared, so that's going to drop out. This is going to give me x times cosine theta, and the other part's going to give me cosine times sine. And then we've got d theta and dx. Theta is going to go from 0 to 2 pi, and x is going to go from 0 to 4. Okay, so integrating this shouldn't be that much of a problem. This part you're probably going to do a u substitution on, but everything should be something that you can handle from there. Okay, so that's a couple of examples of cylinders, and these cylinders are going to be where we're integrating a cylinder that is in different orientations. So if it goes at the x-axis, your parameterization is going to take care of everything that you're going to do in here. Right, I wanted to show you the way the book does this because I think that when we get to spheres, that's going to be very beneficial. Okay, so I do want to get started on the stuff with spheres and just kind of show you what's going to happen if we proceed with this same type of steps and see how messy it gets. And I think that we're going to find that with spheres, it's going to be worthwhile to just kind of memorize something. Right, and the other idea with spheres is that we don't have different orientations. Because of the symmetry of a sphere, you know, if I look at this from different angles, we're still going to end up with exactly the same sphere, so the parameterization is going to be the same always. Alright, so let's say that I have a sphere, and I want to find the flux over this sphere. Let's say that this sphere is a sphere of radius 2. Okay, centered at the origin. Okay, so on this one, the radius is equal to 2, centered at the origin, and let's make this one, the vector field is F is x, y, z. Okay, this is the vector field that just radiates outward from the origin, so we'd expect that the flux on this one, if the orientation is outward, that we'd expect the flux on this one to be a positive number. Alright, so I want to first of all just walk through the first part of this if we proceed with the way that we've done these before, and that is to look at the parameterization for a sphere. Alright, and so if you go back to what we did in spherical coordinates, and you remember that x is equal to rho sine phi cosine theta, alright, and in this case we're saying that rho is equal to 2, so x is going to be equal to 2 sine phi and then cosine of theta. Y is equal to 2 sine phi times sine of theta, and z was equal to rho, or 2 cosine of phi. Alright, go back and look at spherical coordinates. Those are the formulas that got us from rectangular coordinates into spherical coordinates. And remember what these thetas and phis are. Theta is going to be measured around this way in the xy plane, and phi is the one that's measured from the vertical z-axis down to the bottom. Alright, so if you think about what are the limits of integration on this, well, we're going to end up with a theta and a phi plane, and the limits on this are that if we're going all the way around the circle, or all the way around the sphere, theta is going to go from 0 to 2 pi, but phi only goes from 0 to pi. Alright, so like before, here's a point that's in this plane is going to correspond to a point that's on the sphere. If we move in the theta direction, okay, remember theta is going to measure an angle that goes around counterclockwise in the xy plane, so this is going to produce a graph that looks something like that. And then if I move in the positive phi direction, all right, remember that phi is measured from the positive z-axis down to the bottom to the negative z-axis. So as phi increases, actually this is going to move in this direction. Okay, and I want the orientation to be outward, so it looks like I want to take r phi and cross with r theta. Okay, in other words, the green vector crossed with the red vector. The red hand rule says that that vector will be pointing outward. Alright, now here's where this is going to get messy. We're going to take the derivative of these with respect to phi, so r phi is going to be the derivative of 2 sine phi is going to give me 2 cosine phi times cosine of theta. The derivative of the second one is going to be 2 cosine phi sine theta. And then the derivative of the last one is going to give me negative 2 sine of phi. And then if I take the derivative with respect to theta up here we're going to get negative sine of theta times 2 sine phi. So negative 2 sine phi sine theta. The derivative of this one is going to be 2 sine phi times cosine theta. And the derivative of this one with respect to theta ends up being equal to 0. Okay, finally we get something nice there. Alright, so I, J, K. Alright, we're going to take the cross product of this, and I think that you can anticipate that this dA is going to be r phi cross r theta times d phi times d theta, and I think you can see that this is going to become just a mess. Alright, so I want to stop there and leave this for Friday's lesson. So on the homework, you're going to finish up section 19.2, but the problems I want you to do are only the problems that involve surfaces that can be defined something like this, okay, where you've got one variable as a function of the other two, and then the other kinds of problems I want you to be able to do are the ones that involve cylinders, and we'll save the ones for spheres for Friday. I'm sorry, for Thursday. Okay, so you should be able to get through almost all of section 19.2. I will see you guys tomorrow. I'll take questions on 19.2. I'm anticipating there will be a few questions on these kinds of problems, and then I'm going to wrap up the stuff with spheres on Thursday, and then Friday we're going to move on to section 20.1, get into chapter 20. Okay, all right, so have a good day, and I will see you all tomorrow in class. All right, thanks, bye.